Good morning, everyone. This is Dr. Shankaraiah, Department of Physics. Today, I am going to discuss about de-Broglie hypothesis and wave-particle duality in quantum mechanics. So, in the last lecture, I have discussed about the failures of classical physics and then birth to the new branch of physics called quantum mechanics, where we have discussed the three different experiments, starting with black body radiation, photoelectric effect, and atomic stability, where classical physics failed to explain, and by treating radiation as wave. Then Planck gave the new idea that don't treat radiation as a wave, treat radiation as a set of energy particles called quantum. So, so that is the new idea, and using that new idea, Planck's new idea, Einstein and Bohr used the Planck's idea to explain photoelectric effect and atomic stability. So in the end of the session, we asked a question that does the matter also behave as a wave? Because we initially in the classical physics, we used to treat radiation as a wave, but then we found out that we have to treat radiation as set of particles to explain black body radiation, photoelectric effect, and atomic stability. So the question is that matter which we treat as particles in classical physics, so does the matter behave as waves in quantum mechanics? So that is the question we are going to answer in today's lecture. So before going into the details, we need to discuss what are the waves and what are the particles, right? So light is treated as a continuous wave to explain the phenomena of interference, diffraction, and polarization. And light is treated as a beam of photons to explain the photoelectric effect, Compton effect. So we are going to treat light as a wave to explain some phenomenon, for example, interference, polarization, diffraction. Similarly, we have to treat light as a wave, photons, beam of photons, as particles to explain photoelectric effect and Compton effect. So the particle nature and wave nature appears mutually exclusive, right? Neither of the modes can separately explain all the experimental facts. So you cannot use or you cannot treat light as a wave and as a particle to explain any experimental result at the same time. So you have to explain light as a wave, or either as a wave or as a set of particles to explain any experimental result. So that is why we are saying that the particle nature and wave nature appear mutually exclusive, right? And light exhibits both wave nature and particle nature, and this is called as wave particle duality that we have discussed in the last lecture, where we have treated light as wave as, and we also explained light as a set of photons, right? So light or radiation behaves as waves and particles, so it has wave. This is called as wave particle duality. So what is a particle? So a particle has mass m and is located at a definite point, and it can move from one place to another place. So it gives energy when slowed down or stopped. The particle is specified by mass, velocity, momentum, p, and energy. So the motion of this particle can be explained by Newton's second law of motion. So we are saying that particle can be identified by a fixed mass. It has a fixed mass and it is located at a definite point r. And if you apply any force, this particle is going to move from one place to another place. If you apply some force F, point A, and this is point B. Okay. So when it is stopped and when it is slowed down in the momentum, then it is going to lose some energy. So how are we going to specify this particle? Apart from mass and position, we can use velocity, we can use momentum, we can use energy, right? So using this, we can also study the dynamics of particle using Newton's second law of motion, which is given here. F is equal to dp by dt, or which is m into dv by dt, because p is momentum, which is equal to m into v. So I am writing p as m into dv by dt, or dv by a is acceleration, which is equal to dv by dt. So using Newton's second law of motion, we can study the dynamics of these particles. Yeah, so this is all about a particle. So what is a wave? A wave is not located at a definite point like a particle. Instead, it is spread out over a relatively large region of space. Like particle, you can find out the particle at a fixed point A. If you apply some force, it is going to move from to another point B. If you apply some force, but this is a particle. But wave, you cannot. This has fixed mass m. But wave is, you cannot specify. Wave is not located at a point A. You cannot locate a wave at a fixed point, but instead it is spread in region of space. Okay, so this is where you can define wave. Okay, you can specify the wave by frequency, wavelength, phase velocity, amplitude, and intensity. So like particle, we have specified by mass, momentum, velocity, and energy. We can specify the wave by frequency, wavelength, similarly phase velocity, amplitude, and intensity. And the displacement of this wave, so this wave can move in this direction or in this direction, forward or backward. So the displacement from this point, the displacement regarding this wave is given by this equation: y is equal to a sine omega t, where y is the displacement, a is the amplitude, and omega is the angular frequency. Okay, so this is about a wave. So we have discussed about what is a particle and what is a wave, because we want to understand what is this wave particle duality we came across. So de-Broglie hypothesized or proposed that in 1923, wave particle duality is not restricted to radiation. Not only radiation has wave nature and particle nature, but it must be universal. This wave particle duality must be universal. And he said that all material particles should also display a dual wave particle behavior. That is, the wave particle duality present in radiation must also occur in matter. So we are saying that light has wave nature, and this is used to explain interference, diffraction, and polarization. Light also has particle nature. This nature is used to explain photoelectric effect and blackbody radiation. So light, which is radiation, so radiation has both natures. So then de-Broglie proposed that similarly matter should also have this wave particle duality that is present in radiation. So that is what he proposed. So if and as per de-Broglie, if a matter is going to behave like a wave, okay, each material particle of momentum p behaves as a group of waves called matter waves, whose wavelength lambda and wave vector k are given by this equation. Lambda is equal to h by p, where h is Planck's constant. So here h is Planck's constant. And p is momentum. So de-Broglie said that if any material particle is going to behave like a wave, this material particle is going to have a wavelength lambda that is equal to h by p, where h is Planck's constant and p is momentum. So p is momentum, so I have written instead of h by p, I can write that as h by mv also. So this is called as de-Broglie relation. Lambda is equal to h by p or h by mv is called as de-Broglie relation, de-Broglie wavelength of matter waves. So if a material particle having a wave nature, and those waves are called matter waves. So the waves that are associated with a material particle are called as matter waves. So how do we get this relation lambda is equal to h by p? So using Einstein's and Planck's equation, we can derive this de Broglie's equation. For example, we know that from Planck's theory, we know that energy of each quanta is equal to h into nu. Nu is frequency, so this we can write it as hc by lambda. Nu we can write in terms of wavelength. So this is as per Planck. Okay. So as per Einstein, we know that energy of a material particle is mc square. Okay. So these two equations must be equal, and so hc by lambda, hc by lambda must be equal to mc square. So c will cancel out. So we basically have lambda is equal to h by mc. So where c is the velocity of light, light is made up of photons. So if you have a photon, this photon is going to have a wave nature, and this is the wavelength of a photon. But if you have a general particle, for a general particle velocity is v, so lambda is h by m, which is de Broglie wavelength. So this is how we derive this de Broglie relation or wavelength of matter waves using Planck's equation and Einstein's relation. Okay. So we can write down this de Broglie wavelength lambda in terms of kinetic energy also. We already know that the kinetic energy of a particle is given by this of mv square, where v is the velocity and m is the mass. Right. So multiply this equation by both sides. Suppose I have E is equal to half m into v square. So I am going to multiply by v m on both sides. So me is equal to half m square v square. So 2me is equal to p square, where p is mv. So I have m square v square. So that will become p square. So basically p is square root 2me, where E is kinetic energy, not total energy. We are considering E as kinetic energy. So I am going to replace this P momentum in the de Broglie relation. De Broglie relation is lambda is equal to h by p. Right? So where p is momentum. So now for this particle having kinetic energy E, I have momentum in terms of kinetic energy. So that is square root 2me is the momentum. So lambda is equal to h by square root 2me, where E is the kinetic energy. So for a particle having kinetic energy E, you can write down the de Broglie wavelength, which is equal to h by square root 2me. Now, if this material particle is a charged particle, so what is the de Broglie relation? Now, so if the material particle is a charged particle with charge q, then if you have a charged particle, then there will be a potential difference given by v, and then the kinetic energy can be written as E is equal to q into v. V is the potential. V is the potential and Q is the charge. So now we know for a charged particle what is the kinetic energy. So we are going to substitute this kinetic energy in this equation, h by square root 2me. So E is basically Q into V, right? So E is basically Q into V. So that is why I get h by square root 2m Q into V. So this is the de Broglie wavelength for a charged particle. So in this equation, in this slide, we have basically derived de Broglie wavelength for a material particle having some kinetic energy, and then we also derived the de Broglie wavelength for a charged particle also. Using this de Broglie hypothesis, we can explain why only certain orbitals exist. Why not many orbitals? Using de Broglie's hypothesis, right? So in Bohr's atomic model, he said that the angular momentum is quantized. That means angular momentum L is equal to nh cut or nh by 2 pi. So that is what Niels Bohr used in his atomic model. So this is quantized. That means n is integer, you have only some discrete values or discrete values of angular momentum. So L is angular momentum, so this can be written as r cross p. So p is momentum, so basically you have mvr is equal to nh by 2 pi. Right? So you take this 2 pi this side, and then you will get 2 pi r is equal to nh by mv, where r is the radius of permitted circular orbit. Now using de Broglie relation, lambda is equal to h by mv. Right? So this h by mv is nothing but lambda. So you substitute 2 pi r. So 2 pi r is actually equal to n into lambda. So the orbitals, the circumference of the orbital 2 pi r is equal to n into lambda. Lambda is the de Broglie wavelength and n is integer. If the orbital wavelength or circumference is an integral multiples of this, integral multiples of wavelength, only that orbital is stable. I can have orbitals, orbitals whose circumference is 2 lambda. For example, this. I can have orbitals circumference whose orbital whose circumference is 4 into lambda is this. So you have only certain orbitals whose circumference is always equal to n into lambda. So we can understand this de Broglie's relation. We can use this de Broglie relation to understand the Bohr's atomic model and orbits. So what are the properties of these matter waves? So we have said that the waves that are associated with a material particle are called as matter waves, and we have discussed what is a particle, what is a wave, and then we have derived the de Broglie wavelength in terms of kinetic energy, and for a charged particle, what is the de Broglie wavelength of some charge q and experiencing potential v. And then we've also used this de Broglie wavelength to understand these orbits, why certain orbitals are stable. So let us now discuss the properties of matter waves. Okay, so first, lighter is the particle. So we are saying that particle waves associated with the particle are matter waves. So if this particle is lighter, then the value is small, right? So then lambda will be large. So lambda is equal to h by mv. So if m is small, lambda will be large. So that is why, therefore, wave behavior is significant for microparticles. Only if mass is less, then lambda is high. Then you can find out the lambda and you can detect this wavelength, and this is significant. But if mass is large, for macro bodies where you have mass of some grams or kgs, then wavelength is very small, it goes to 0, and you cannot detect these de Broglie waves or matter waves associated with macro bodies. So the matter waves are associated with the microparticles having very small mass, okay, so that we can find out or detect this wavelength. Suppose if the velocity is 0 and then lambda is infinite, because lambda is equal to h by mv. So if you are taking velocity 0, then this wavelength is lambda. So waves become indeterminate. So this shows that matter waves are generated only when the particles are in motion. If the particle is in rest, then v is 0, lambda is infinite, you cannot detect this. So when the particle is moving, only then you can find out these matter waves associated with this particle. Okay, so smaller is the velocity of the particle, greater is the wavelength associated with, and it will be easy for us to detect these matter waves associated with a particle. So we have discussed about 3 important points here. So matter waves are associated with only microparticles, not with macroparticles, and matter waves are associated with the particles in motion, right? Not particles at rest. Yeah. So matter waves are independent of charge, right? They are neither electromagnetic waves or not. They are not electromagnetic waves. They are not acoustic waves, but they are new kind of waves. Okay, and we can show that these matter waves travel with a velocity of faster the velocity of light. the velocity of matter waves is greater than the velocity of light. Okay. So these are some properties of matter waves that we have discussed here, and this is very important. Okay, so up to now we have discussed about properties of matter waves. So these matter waves, we have to prove them. I mean, so we are saying that matter has a wave nature, so we need to prove that these particles behave like waves. Okay, so this is done by Davison and Germer experiment. So both the scientists, Clinton Davison and Lester Germer, independently carried out this experiment on matter waves, and they proved that in their experiment that matter waves do exist in nature. So this is the experimental arrangement. So you have a electron gun that is connected. This is the electron gun connected to a battery, and electron gun connected to a battery. Okay, electron gun connected to a battery, and then there is a target which is a crystal, and you have a scale here, rotating scale, and you have an electrometer to count the number of electrons. So using this electron gun, you can shoot the number of electrons onto this target crystal, and then these electrons are scattered in different angles. The electrons are scattered in different angles from this crystal, and you are going to look at the scattering angle of this electron. So there is an scattering angle. Okay, so there is scattering angle phi. So you are going to look at the scattering angle phi of each electron, as well as you are going to count the number of electrons using this electrometer. So that is what Davison and Germer did in their experiment. Okay, so using this experiment, so they have calculated the scattering intensity and scattering angle of all the scattered electrons from the nickel crystal. So they have plotted this scattering intensity versus scattering angle, and they found that there is a peak in the distribution around some angle 50 degrees. Okay, so electrons are the scattering intensity is maximum. That means there are more number of electrons that are getting scattered at an angle of 50 degrees, right? So this is Bragg's diffraction that we will use later, right? So but here Davison and Germer found that why there is a peak in the scattering intensity at an angle of 50 degrees. Okay, so in their experiment they also changed the potential. They have connected this electron gun to a battery, so they can change the potential using this battery. So they have changed the potential, and they measured this scattering intensity for different potentials or voltages, right? So they have plotted this here for different voltages. So 40 volts, 44 volts, 48 volts, 54 volts, 60 volts, 64, 68. So they found that the maximum peak in the intensity is around 54 volts. So around 54 volts they found there is a peak, and above the 54 you can slowly see that is a decreasing of this peak, right? So something strange is happening around 54 volts in the intensity. So that is what they wanted to understand. They found that in the beginning, they found that at 50 degrees of scattering angle, there is a peak in the scattering intensity, and then by changing the voltage, they found that this peak in the scattering intensity is occurring at a voltage of 54 volts. So what is happening at this potential and at the scattering angle of 50 degrees? Okay, so using de-Broglie relation, because this is a charged particle electron is a charged particle, right? So it has charge Q, and V is the potential that is experienced, or voltage here, right? So using de-Broglie relation, we can calculate the wavelength where h is Planck's constant, right? Here h is Planck's constant, Q is charge of the particle, V is potential, M is mass of the particle. Okay, So electron is a charged particle. So using this de Broglie relation, we can calculate wavelength. We know all the values. For example, Planck's constant H is 6.626 into 10 power minus 34 joule second. I'm not writing the units here. Q is 1.6 into 10 power minus 9 electron, and similarly mass M is 9.1 into 10 power minus 31. And we already know that the voltage where we see the peak in the distribution is 54 volts. So substitute all these H, Q, M and V in this equation, and we can get the value of 1.66 angstroms. So this is the wavelength using de Broglie relation. But this is a theoretical proposal. We want to compare this theoretical equation with an experimental relation. Okay, so that that can be done using Bragg's equation. So Bragg's equation is 2d sin theta is equal to n lambda, where d is interplanar spacing, right? D is interplanar spacing. Interplanar spacing, the distance between all these parallel planes. So this is the distance d between the parallel planes, interplanar spacing. So in this experiment, they have used d as 0.91, the interplanar spacing for this nickel crystal. So they are using nickel crystal. The interplanar spacing is 0.91 angstroms, and the diffraction angle is 65. So how did we get this? Let us look into this. Let us look into this diffraction angle. How did we get this diffraction angle as 65 degrees? So if you know that diffraction angle is 65 degrees, then we can calculate lambda using this Bragg's equation, and then we can compare the lambdas from the experimental Bragg's equation and theoretical de Broglie relation. All we want to know is that how did we get this angle 65 degrees? So that is what we want to understand now. Okay, so that we are going to understand from this picture. So these are all crystal. We know that we have considered nickel crystal, right? So yeah, so let me erase here. Nickel crystal we are considering. So these are all parallel planes. The distance between parallel planes is d. Okay, so we know that the scattering angle, the maximum scattering angle is 50 degrees. So it is coming and getting scattered. So this is coming here in this direction, electron is coming here and it is getting scattered in this here, in this angle. So maximum angle is 50 degrees. So if I draw a normal for this plane, so this is 50, so it is equal on both sides. So that is 25, totally 50 degrees. So that is what we found. So now from this, we are going to look at the diffraction angle. Okay, so this is normal, so it must be 90 degrees. So, right, so 90 degrees, so this is 25. So 25, this must be 65. So that this angle, this is the diffraction angle, right? So this is the angle of diffraction. So this is 65 degrees. How did we get this 65? Because it must be 90, but we already have here 25 degrees. So 90 minus 25, it is 90 minus 25. 90 degrees minus 25 degrees. So we have theta as 65 degrees. So using this picture, you can understand how did we get this scattering angle. Diffraction angle as 65 degrees. So we are going to substitute this diffraction angle 65 degrees in this Bragg's equation. So Bragg's equation is 2d sin theta is equal to n lambda, but we want lambda. So lambda is equal to 2d sin theta by n. So we are taking first order. N is actually order of diffraction here. N is order of diffraction. Order of diffraction. Here we are taking the order of diffraction, n is equal to 1. So only the first order diffraction. There is no second order of the order diffractions here. Only one first order diffraction. So substituting this all the values which we know, from this Bragg's equation, which is lambda is equal to 2d sin theta by n. So then we get the value lambda as 1.65 angstroms. From the de Broglie relation, we have lambda as 1.66 angstrom. So from these both One is experiment and one is theory. So from both relations, we found out that the wavelength is matching. That means that the beam of electrons that are shooted from electron gun, behave like waves. That is what we get from this experiment. Okay, so here in this slide we proved that de-Broglie wavelength and the wavelength that we get from this Bragg's equation are matching. Okay, fine. Yeah, so the value of the wavelength of electron is found to be in good agreement with both theory and experiment. That is, a beam of electrons behaves like a wave. Hence, Davison and Germer experiment verifies the de-Broglie concept of matter waves. So we found out that from this, we found out that even we are shooting the electrons from here. Electrons are particles. Okay, so these set of particles are going to behave like wave. That is what we proved in this Davison and Germer experiment. So in this lecture we have discussed about wave particle duality and de-Broglie hypothesis. So we so in this topic, from these topics, we first started with what is a particle, and then we said what is a wave, and then we have discussed the matter waves properties, and then we in the experiment, Davison and Germer experiment, we proved that these matter waves do exist in nature. So the next question is that are these matter waves harmonic in nature? So that is the next question which we are going to answer in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.